Hello everybody. So lesson 7.7, this is for writing equations for higher degree polynomials. So first thing we should start out with is what is a higher degree polynomial. So this is any polynomial that has a degree that's higher than 3. So we know we have would help if I started out with writing. So we have quadratic, right, has leading term of x squared, and then we just learned cubic in the last section has the leading term x to the third. So higher degree simply means the leading term, let's say term's exponent is higher than 3. So anything that's x to the fourth, x to the fifth, x to the sixth, and so on would be considered a higher degree polynomial. We don't have a special name for it like quadratic or cubic. It's just a higher degree polynomial, 4th degree, 5th degree, 6th degree. Okay, the next question we need to know are extreme values. So extreme values I mentioned in class when we were discussing 7.6. When you have a graph, anything, doesn't matter how many times it turns, whatever it does, your extreme values are your maximum and your minimums. Okay, so these are your maximums and minimums. You can think of them as turns or bumps. Okay, and I'll reference these extreme values because these will be very helpful in deciding what degree polynomial we have. Okay, so now for steps on how to write the equation. We have 5 steps here, and with a couple of examples in between. So I left you a lot of room. Hopefully it'll all fit. So how to write the equation from the graph of a polynomial. So let's start out. 1, you need to find the lowest possible degree of the polynomial. So find the lowest possible degree of the polynomial. And the way you do this is by count the number of extremes and add 1. Okay, so as an example, if you have something that looks like this, we already know this to be a cubic function. If you look at the number of extremes that are here, we have, we have 1, 2. So 2 extremes plus 1 equals 3rd degree. Okay, so something that would look like this. Okay, just making anything up right now just to show you. So here we have 1, 2, 3, 4. So this is 4 extremes plus 1 equals 5th degree. And that's the lowest it could be. It could be higher, but that's the lowest it can be. Okay? That seems pretty simple. Number 2. Find the roots. And this we practiced already in 7.6, so you should be experts at this. Remember, your roots are your x-intercepts. Okay? And so you would see, you would find roots. So here's an example of the graph. And we have an example of a double root, so I'll show you what that would look like. Let's go like this. Okay, so here we have a regular root, a regular root, a regular root, and this is a double root. So let me just make a couple of notes here. So I'm going to point. This is regular, 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 and this is double. Okay, so what is a double root? So let's make this notation here. Special note. If the part of the graph with the root does not cross the x-axis, then it's a double root. Okay, so meaning as you watch this line, oh, and I forgot a root here. Hopefully you guys caught that. There's a root right there too. Silly, silly. There's another regular root. Okay, so as you watch this line, you see this line goes through, crosses. So there's a root. This line goes through, crosses. There's a root. Crosses. There's a root. Crosses. There's a root. This one goes down, just touches, and then gets turned away, turned back up. That's what makes a double root. Okay, so it doesn't cross the x-axis, it just simply touches it and then turns away. So that means that you have a double root there, which means instead of, let's say, this being just a root at 2, there's 2 roots at 2. And we'll go through an example that has that. Okay, so that's step 2. 3 more steps. Hopefully you've left enough room. Otherwise, grab another sheet of paper. So step 3, these ones aren't as long. They don't have examples. So step 3, write factored form. So you have y equals a times x minus root 1 times x minus root 2 times x minus root 3. And this can keep going. You can have x minus root 4. Depending on how many roots you have will depend on how many sets of parentheses you have. So these depends on number of roots. If you have 7 x-intercepts, then you're going to need 7 sets of parentheses. Step 4 is to find another point on the graph and substitute to find a, just like we did for the cubic functions. So find another point on the graph, remember x, y, and substitute into the equation and solve for a. That way we can find that vertical scale factor. Okay, and then step 5 is just to rewrite the equation plugging in a. So step 5, rewrite the equation by plugging in a. Okay, these are going to be very important steps to have for the entire section 7.7, and it'll also help you with 7.6. So make sure if you didn't write these down, including the examples, make sure you please pause now, rewind, go back and do that, because we're going to get into using these steps to complete a couple of examples now. Okay, so on the back, writing the equation of polynomial function in factored form and general form when given a verbal description. So we're going to use the same steps as for example A, but most of the work's already done for you. So, oh, sorry, I went to the wrong page. Just kidding. How about we start with example A? So example A says, write the polynomial equation of the graph below. And of course I didn't put in a graph. Okay, fabulous. So let's draw a graph. We'll just draw one quickly. Okay, example A. Doesn't have to be perfect, but we'll get the idea. So you're going to have a graph that looks like this. I'm just going to go, these are counting by ones, so we'll go 4 that way and 4 this way. And I will draw something that looks like this. Oh, do I have to go further? I do have to go further. Sorry, we need a fifth We need a fifth line over here. Okay, so here we go. Let's go down. I'm going to start by going, yeah, that's fine, down this way, and then up to here, and then back down, and then up to here. Okay, so I didn't do a fabulous job. This should cross here, and then this should cross here. So we should have intercepts, x-intercepts at those points. Okay, so if you can do as good a job as me at drawing the graph, you're in a good spot. So sorry about that, the picture not being there. So let's look at the first step. So the first step is to find the lowest degree of the polynomial, and we do this by counting the extremes. So we have 1, 2, 3. So we have 3 extremes. Whoops, plus 1 means we have a 4th degree polynomial. Okay, so that's step 1. Step 2 is to determine the roots. So we have x equals -4, that's right here. We have x equals -2, that's right here. And since this point isn't crossing, since our line is not crossing the x-axis, that means this is a double root. And then we have this one here, which is x equals 1, 2, 3, 4, 5. So we have 4 zeros, or 4 roots, okay, which makes sense because we have a 4th degree polynomial. So step 3, let's write this equation out leaving a alone. So y equals a times x minus 4 times x minus 2 times x minus 2 times x, oh, that's minus -4, so plus minus -2 plus minus -2 plus, and x minus 5. So there's up to step 3. I'm going to move on to another slide so that I can solve for a. But I need to find a point, another point on this graph. So the other point on this graph, we'll have to write it in because, again, I forgot to add the picture. So the other point on this graph is here, and this is 0, -80. Okay, so we're going to take that other point on our graph now and complete step 4, which tells us to plug in x and y. So I'm going to rewrite this equation. So I have y equals a times x plus 4 times x plus 2 times x plus 2 times x minus 5. And the other point that I'm using is 0, -80, so this is my x and my y. So I'm going to plug those numbers in. So y is -80 equals a times, so 0 plus 4 is 4, 0 plus 2 is 2, 0 plus 2 is 2, and 0 minus 5 is -5. And multiplying all of those together, we get -80. I have a times -80. Well, dividing by -80 to solve for a gives me +1. All that work to find out a is 1. Well, that's okay. So our final solution then, we write y equals, put in a, which is 1, times x plus 4 times x plus 2. I'm going to square this, because x plus 2 times x plus 2 is the same as saying x plus 2 squared. So now this is a little bit simpler than having all 4 written out. You'll see it written with just the squared there. And then this would be x minus 5. And this will be our final answer for that more complicated graph. Okay? All right. So moving on to the next example. Oh no, not the next example yet. So how to describe end behavior of a graph. So what is end behavior of a graph? Well, it's pretty simple. You're looking at where the end of the graph is going. So for example, back in example A, how would we describe end behavior? So it's exactly what it sounds like. Here's the graph, here's one end. What is happening in that end? Well, as x is decreasing, right? X is decreasing because we're moving to the left. What's happening to y? Well, y is increasing. So that's your end behavior. We talk about going to infinity because, as we know, numbers never end, and on a graph we only see a piece of the function. So what's happening here is as x goes to negative infinity, y is going to positive infinity. And then we look at the other side. Here's the other end of our graph. And as x goes now to positive infinity, what's happening to y? Y is again going to positive infinity. So end behavior is just looking at your two outside pieces of the graph and deciding what's happening. As x decreases, what's happening to y, and as x increases, what's happening to y. So I guess that's the best way to write for end behavior. End behavior is talking about what's happening at each end of the graph. So you'll have as x moves to, that's a v, as x moves to negative infinity, y does what? Does it move to positive infinity or negative infinity? So is it going up? That would be positive infinity. Or is it going down? That would be negative infinity. So y moves to, and then you would fill in the blank. Then you would continue to say, as x moves to positive infinity, by the way, I'll put this in here. Symbol for infinity, if you don't know, is like a sideways 8. So as x moves to positive infinity, you would say y moves to, and then again you would describe what happens. Does y move to positive infinity or negative infinity? Okay, so that's your end behavior of the graph. All right, finally on to example B. I keep wanting to rush this. Writing the equation of polynomial function in factored form and general form when given a verbal description. So it's the same exact steps, but most of the work is already done, which is nice. So if you look at example B, it says write the lowest degree polynomial function that has the given set of zeros and whose graph has the given y-intercept. So they've already found our x-intercepts, and they gave us a y-intercept so that we can write the equation here. So taking a look at example B, number 1, okay, they're telling us that we have zeros at -4, 5, and -2, and they're telling us that -2, I'm just going to put dB, is double. They're telling us the y-intercept, so that's the other point they're giving us, is -80. So y-intercept being -80 means that my x value is 0 and my y value is -80. So we can count up the roots. That's another way to know what degree function we have. So we have 1, 2, 3. It looks like 3 roots, but remember this is a double, so it's actually 4 roots. So we have 4 roots, which means 4th degree polynomial. So my equation will have to have 4 sets of parentheses, x minus, x minus, x minus, and x minus. So I have x minus -4, so that's +4, x minus 5, and x minus negative 2, so that's plus 2, minus negative 2, so that's plus 2. And now to find a, I plug in x and y. So x and y, plug that in. I have negative 80 equals a times 0 plus 4 is 4, 0 minus 5 is negative 5, 0 plus 2 is 2, and 0 plus 2 is 2. Multiplying all that out, I get negative 80. So I have a times negative 80 equals negative 80, and I divide both by negative 80 to get a equals 1. So same example as in example A, but this time they're telling you what's going on. So it's a little bit less work for you because they're giving you the information that otherwise in example A you had to find from the graph. So still not done. Remember, the last step is an important step because this is your final answer. So now that I know that A is 1 and I have this equation here, I'm just putting it together, leaving y and x in and putting in my 1 for A. So for example B, my final answer is y equals 1 times x plus 4 times x minus 5. And remember, x plus 2 is a double, so we can just write it squared. Okay? And that one is done. All right, so let's try one that has some imaginary numbers in it. So this, in these types of problems, you would only get this as a verbal problem. You wouldn't have to find, you can't find imaginary roots from graphs. Okay, so that wouldn't be possible. So let's look at example B, number 2. And here they're telling us that the zeros are x equals negative 5i, x equals negative 1. They're calling this a triple root. And x equals 4. They're telling us the y-intercept is negative 100. Okay, so this is a little bit tricky. First of all, triple root means that I have 3 roots here. I have 1 root here, and it looks like I have 1 root for negative 5i, but this is an imaginary number. And imaginary numbers always come in pairs. Remember what the pair is called? A conjugate. So, a little note here, imaginary roots always, sorry it's squished, come in pairs. And that's our conjugate. So really, when they give us x equals negative 5i, this is x equals negative 5i and positive 5i. So there are actually 2 roots here. So this function has 2, 3, 4, 5, 6 different roots. This is a 6th degree function. Seems like it should be pretty difficult, but it's the same exact steps as we have done before. The expansion is going to be a little bit different because we have the I in there, but we'll watch and see how it goes. Okay, so 6th degree function. So I'm going to go to the next page. I have y equals a. So now I'm going to have 6 sets of parentheses. Okay. So we go back and plug in. We have, like I said here with the negative 5i, we have a negative and a positive. So when I put in the negative, so it's negative, so it becomes positive, 5i and minus 5i. I also have negative 1, that's a triple. So negative 1, so minus negative 1, so that's positive, minus negative, that's positive, minus negative, that's positive. Now, if you don't want to write out the triple, you can just put it to the 3rd power. That's what the shortcut, and that's a lot then you don't have as many parentheses, and since it's a triple root, that's what you would do. So I'm going to simplify this in a minute, but I just wanted to show you this way. And then the last root was 4. So then we would have x minus, and we put in the 4. So this can be simplified to y equals a times x plus 5I times x minus 5I times x plus 1 to the third power. Now again, I don't have to do the step above this. I could have just written that way because there's 3 of them since it's a triple root. And then x minus 4. Okay, so next step, they told us that the y-intercept was negative 100, which means that my point is 0, negative 100. So here's x, here's y. It's always nice if you can use the x-intercept. As long as it's not 0, 0, you can use the x-intercept. Or sorry, it's always nice when you can use the y-intercept. As long as it's not 0, the coordinates are 0, 0, you can use the y-intercept, and then x is 0, which makes life a lot easier coming up here. So from here, I'm going to plug in 0 for all of my x's. So I just end up with 0 plus 5i, which is just 5i. 0 minus 5i, which is negative 5i, 0 plus 1 to the third power, so this is 1 to the third power, and then 0 minus 4 is negative 4. Simplifying further, y equals a, let's multiply these guys out. So we would get negative 25i squared. And we know what to do with that I squared, don't we? 1 to the third power is just 1, and negative 4 is negative 4. What happens with I squared? I squared becomes a negative 1. So negative 25 times negative 1 times 1 times negative 4 is negative 4. So y equals a times negative 25 times negative 1 is positive 25 times negative 4 is a negative 100. So y should have been negative 100 all this time anyway. So plugging in the negative 100 for y, I'm going to come over here. So negative 100 equals a times negative 100. Divide both sides by negative 100. And a equals 1. I promise a does not always equal 1. It just so happens that the two examples I'm doing, a is equal to 1. Okay, and going all the way down here, you might have had the negative 100 in. You probably should have had it in. My fault, but I put it in at the end. Either way we solve, we get a equals 1. So the final solution, we're going to take what a equals, and we're going to take our function from here and put it all together in our final solution for example B. So we would have y equals 1 times x plus 5i times x minus 5i times x plus 1 to the third power times x minus 4. And this is our answer to part B. So again, a little bit longer, a little extra work involved by multiplying all those out with the imaginary number, but we know how to do all of that. That's stuff we've already learned. And that's that. Okay, so we'll do some practice with this in class the next time I see you. And that'll be it.